But first, some things you need to know.
Tegan is Sarah, Sarah is Tegan, Mr. V likes planks, Mr. Mignia likes scissors. Reese is also Brighton.
Alright guys, calm down. We're gonna watch a Bill Nye video. Everyone in your seat or I'll dock you in 5, 4, 3, 2, 1. Alright, shh. Watch Bill Nye.
Shouldn't you pull down the screen? You're gonna break it.
15 minutes later.
So, did you guys get that?
No. Well, obviously, because you sped it up since we don't have time, apparently.
Fine, let me explain. The speed of light in a vacuum is 300,000 kilometers per hour, which we will now refer to as c.
Actually, it's 299,792 kilometers per second.
Clayton, you just used one of your sarcastic comments of the week. Moving on, nothing with mass can ever go past this speed. And it's due to an equation which is momentum equals this weird y times mv. Does anyone know what that weird y is called?
Isn't the y called gamma?
Yes, gamma is a ratio, and at normal speeds, like throwing a baseball or riding on a car, it's basically 1, so we just ignore it because that's what we do in this class. Does anyone know what the ratio is?
Square root of 1 minus v squared divided by c squared.
So as you guys know, my slideshow is broken today. I don't know, projector's acting up. That's why Bill Nye was weird. When your velocity gets close to the speed of light, gamma starts going up more and more and more, and you become infinitely more massive until it requires infinite energy to move you any faster. So there's one more important premise of physics that we need to know for this class. The laws of physics stay the same for all non-accelerating observers no matter how fast they're going. So if you're on a plane flying along the sky and the windows are covered, there's no experiment you could perform to figure out how fast you are going.
If you were on a plane and threw a ball up, wouldn't it fly back and then you could tell you were moving?
That's actually a great question. I was gonna address it on the next slide, so stop getting ahead of me. So if you threw it up, it would already have momentum, so it wouldn't fly backwards actually. It would look exactly the same as if you were standing on the ground. These laws have interesting implications, and one of those is called special relativity. Before I explain it, let's do a thought experiment.
Oh, that's why when you stop a car, you feel yourself move forward because you still have the momentum.
Alright, so imagine Clayton is riding on a train, right? And this train is going at the speed of light. Well, close to it, 0.9 c. Tegan, with her good common sense, decides to stay at the train station. They're both holding light clocks. Now, a light clock is 2 mirrors with a photon that bounces back and forth. Every time the photon hits one of the mirrors, that's a unit of time. Doesn't matter what unit of time.
Vacuum, will light travel slower?
Yes, Clayton, you're right, and you've been docked for not using your slips. Let's take a look at the next drawing. So here we see Clayton's time clock, and here we see Tegan's time clock. Tegan's light bounces back and forth only in the y direction. However, Clayton's time clock bounces back and forth in the y and some of the x, as you can see. Clayton's travels a much larger distance in the same amount of time. However, Tegan's travels shorter. Time must dilate to account for this because they are a fixed distance. I see you're all confused, so let's explain this. That's where special relativity kicks in. Time is moving faster for Tegan relative to Clayton, and slower for Clayton relative to Tegan. This means that the universal speed of light is preserved from both frames of reference, both Clayton's and Tegan. There's also something known as length dilation that's kind of odd. I mean, objects contract and get longer the faster they go or the slower they go. It's another thing that we're just going to ignore because it's this class and you can learn about that later. So, but if Tegan measured the length of Clayton's train, it would be shorter than if Clayton measured it from his frame of reference.
Why would it be shorter?
Basically, both time and length dilation are due to the same equation, d equals rt. You guys remember that one, right? It says here that, basically my notes say that just to keep everything like accurate with the speed of light, distance and time have to change because the rate, which is constant, the speed of light can never change. The other variables must compensate. Sarah and Tegan, you've been docked.
But we finally understand!
Mr. V, you're wrong.
No, this actually happens. We use it in real life. GPS satellites, they move pretty fast in orbit, and we have to resync them every night to keep them in time with other types of clocks.
So, let's do one more thought experiment. It's called the twin paradox. It has to do a little more with relativity. So, Clayton gets bored with his relativistic speed train and finds something more dangerous to do. So he steals a rocket that is moving away from the Earth at 0.9 c. He is moving away from the Earth because he has an evil twin who is also the same exact age as Clayton. When Clayton gets bored from doing that, he turns around, comes back to Earth, and is younger than his evil twin.
So what is the paradox, Mr. McNeil?
Oh my god. Well, relativity says that motion is relevant, right? So, how do we know that the Earth, aka evil Clayton, wasn't speeding away from Clayton? This is why Einstein said that the laws of physics are the same for non-accelerating observers. Real Clayton is changing direction when he changed his mind, and a change in direction is acceleration. This is how we know that Clayton has aged less.
Wouldn't we age the same, but it would feel longer for my evil twin?
Now that's a good question, for once. Neither you or your evil twin would be able to tell if time was going faster or slower, but more of it would pass for your evil twin, and in fact, he would age longer.
Mr. Mignia, just put Bill Nye on normal speed.